So we have transformations of functions, and we know how to move it up. We know how to move functions upward, or we know how to envision what would happen if we add or subtract certain numbers, whether it be inside the function or outside of the function. If you add or subtract a function with a number on the outside, then you produce a vertical shift upward or downward. If you add or subtract a number within the function with only x, then you move it to the left or you move it to the right. And if you multiply a number on the outside of the function, and depending upon what that number would be, it's either a vertical stretch or vertical compression. If you multiply the x value by a certain number, depending upon what number it is, whether it be bigger than 1 or less than or equal to, or between 0 and 1, you would produce a horizontal shrink or a horizontal stretch. And then obviously when you have these negative symbols, they create reflections. So either you reflect across the x-axis or you reflect across the y-axis. So that's what we were doing last time. And we were trying to apply these different transformations upon parent functions. And then we spoke about combinations of functions, right? We talked about the sum, difference, product, and the division of functions. And we discussed how the notation looks like, the function notation for each kind of operation. And we also discussed how to figure out the domain, which is really just a intersection of the two functions. So what we left off on was this idea of composition of functions. And this was a very special operation that functions are utilized, or we're able to apply this operation upon functions. And we just simply talked about it as a little introduction last time with this example. So this is lecture number 7. Today is the 24th of February. So we're going to continue with this idea of composition of functions. So if you look at the previous example, we have this function here. It's f of x equals x plus 2, a very straightforward function, a linear function. So when we plug in x and we plug it into this function that we call f, the result will produce x plus 2. Now the idea is, what if I apply this function to itself again? So after I applied it once, and whatever I get as the output, put it back into itself, which I could do. And then if I do that now, what does this become? This becomes the input of my function again. But now what am I doing to the input? I am adding by 2 every single time. So now the result will be x plus 4. So we'll discuss more as to how we approach this idea of composition of functions. So first off, we have to talk about the function notation for it. So how do we write this algebraically? So what we do is we start out with 2 functions. So a composition of functions is written functions between 2 functions f and g is written as, what is it written as? It's written as the following: y equals f, I'm sure I like this, f of g of x. Now this also means, or I can write it at this, and this is the more common way, f g of x. So when you ever see this symbol here, f little circle g, what this is really saying, f circle g, is saying that f follows G. Now, when you follow somebody, who is first? Is it the person that you're following, or the person that, or you as the person that's following? So what comes, quote unquote, first, F or G? G, right? So G is first. So the order of this does matter. So in this case, G is first. G is applied first. Then F. Then F is applied. So one way to visualize this, right? To visualize, we use the machine diagram that we spoke about with functions when we started talking about functions, right? So the idea is this. So if I want to visualize y equals f of g of x, what's going to happen is x is going to be placed inside the g function. What it's produced is what? G of x. And then this g of x, so this is the output of g. So the output of g, this is the input of g. And then now this becomes the input. So I'm gonna write this. This now becomes the input of f. And f is here. Let me move this a little bit to the side. And now the output here, what is the output of f? It's f of g of x. So do we see that? So when we envision f of g of x, we apply g first, whatever g spits out as the output. Now that is the new input for f. And then we apply f onto the input, this new input, which is g of x. And then the output becomes f of g of x. And then sometimes how people envision this is, instead of going through this whole machine, going through two different machines, we can just call this one single machine. We can just say, hey, let's go from x and go all the way to this in one full swoop. So, but then this would be called, this would be called a new function. So we can think of this as one big function, and this function is called f follows g. Again, this is just a visualization of what's happening. Okay. So let's see this in action now. So let's suppose, example, let's suppose I have two functions, f of x is equal to x squared and g of x is equal to x minus 3. So the first thing is I want to find f of g and g of f. G follows f. And of course, and their domains. So we have to talk about the domains as well. Okay, so the first guy, right? The first guy is f follows g of x. So what is f follows g of x? Well, we can rewrite this as f is being applied to g of x. We can apply it this way. And then what is g of x though? G of x is defined to be x minus 3. So you see, remember, we can apply, or we can plug in the input to a function, and it could be an algebraic expression. It doesn't always have to be just a number that you plug into a function. You can actually plug in algebraic expressions. So now what am I saying? I'm plugging in x minus 3 to my function every single time I see the input x. So I'm going to replace this x now with x minus 3 instead, because my input is x minus 3. So this is going to be squared, and this is going to be x minus 3. And then if you'd like, you can expand this, right? This becomes x minus 3 multiplied by x minus 3. And when you distribute everything, you get x squared minus 6x plus 9. And this is the composition of these two functions when g is applied first and then f follows g. Yes, thank you. Wow, you guys are quick. And the question is, why does it get squared? Why does it get squared? Well, remember, this all is based upon these two specified functions. My first function, f of x equals x squared, and my second function, g of x, is x minus 3. And what am I doing? I'm taking one function and plugging it into another function. Which function am I plugging into? Well, g of x, remember we apply this first. What is g of x? Well, it's written here to be x minus 3. And what am I doing to g of x? I'm making this the input of f. So g of x can be replaced with what we defined it as, x minus 3. Now, what is f? What does this function do? Well, this function is defined to be the function that whatever input you plug in, you have to square it. In this case, it's not just the x that you're squaring. In this case, you're squaring the expression x minus 3 by the very definition of the function f. So therefore, to evaluate this, I must square x minus 3 because of the way f is defined in the beginning. And that's why we square it. No, it's okay. Don't worry. Please ask any questions you may feel, because there are many people out there that might have the same question and it might benefit them. And so then what would be the domain? So what would be the domain of this function? And this gets kind of tricky when the functions themselves are not as straightforward. But because both of these functions have both of these functions here, well, the domain and range for g is all real numbers. Why is that? Well, g of x is a line. It's a linear function. Now, what's the domain here? The domain here is also all real numbers. And the range here would be from 0 to infinity. But we only care about the domain. So what happens with the domain of this function? Well, in the very beginning, the domain is all real numbers. What you produce is all real numbers. And this checks out with the domain of this function f. So because all of these check out, then the domain here is non-alterable. It doesn't change. We don't have to worry about anything. It's very nice. The domain is all real numbers as well. Everything works for this problem, for this function. We'll get to examples where it's not that clear and it's not that nice. So Alexander, what I'm saying is, I want to find the domain of this function here. Remember, this is a composition of functions, so it's one applied after the other. I'm trying to look for what's the domain of this new function. So in order to understand this new function, I must understand the pieces that go with it. So each of these functions have a certain domain and range. What so happens is that these functions, for example, this linear function here, is very nice in the sense that the domain is all real numbers, the range is all real numbers. So whatever I plug in for this function here, g, the possibilities is going to be all real numbers. Now, in terms of the output, so all of these outputs are everything. everything on the number line. Now, the output of G becomes the input of F. Because the range of G, which is the output of G, becomes the input of F, and since the output and the inputs coincide, there's no problem here, right? So these coincide. There's no discrepancy between these domain and the range of G of X. So you have to be mindful. To find a domain, you need to be mindful of everything that G produces and compare that with everything that F takes in. So if there's no discrepancy there, then we would have to say that domain for this function that we get at the end is everything, all real numbers. But it's a very key point. Now let's do the opposite. Let's do the switching the order. So what happens if we do G follows F instead? Would it be anything different? And most likely it would be. So the composition of functions, one thing we're going to notice is that the composition of functions are what are called not commutative, meaning that the order does indeed matter. We cannot say that the order results in the same thing because it won't. So G follows F. Now it's completely different. F is first. So now I'm going to rewrite this as G of F of X. So what's G? Well, first of all, what's F? F is X squared. Sanjana, the quiz is at 10:15. So you have about an hour and 10 minutes till the quiz. Okay, so G of X squared. Now what's G? Well, G is everything that you plug in, you just subtract by 3. So whatever input I got, I subtract by 3. Well, what's my input? It's X squared. So then what's going to be my output? X squared minus 3. And so therefore, this compositional function up to these two functions is X squared minus 3. And then what happens? What's the domain of this function? Well, again, let's study this idea. What's F? What's the domain of F? Well, I just wrote it here, didn't I? The domain of F is all real numbers. And then the range for X squared are only positive numbers. And now this guy here is gonna become the input for G. But because this range, right, is inside of the domain of this function, that means that everything that I produce for F can go into G. Everything works. And so therefore, the domain is indeed, again, all real numbers. Like I said, these functions are very nice. They don't produce any problems. Everything is beautiful in this world. And let me just say, so note, F follows G of X is not necessarily G of F of X. So composition of functions is not commutative. Order, switching the order does affect the result. Switching the order does affect the result. Okay? So that's what we realized from this simple example here. All right, awesome. So that's part A of this problem. Now part B. What if I want to evaluate? So evaluate the following. What if I want to evaluate F follows G of 5? Now I want to find a specific I want to find a specific numerical value. So the first thing, of course, is I want to rewrite this. Rewrite this as f g of 5. Now, how do we approach this? Well, now instead of having variables, we have numbers. Might be a little bit easier. Again, what comes first? G, and then what comes after? F. So first I have to figure out what is g of 5. Well, what is g? G is x minus 3. So g of 5 is 2. So I still have this f on the outside, but on the inside, I'm going to replace it. I'm going to evaluate it. G of 5 equals 2. And now that 2, which is the output of g, becomes the input of f. And what's f now? Now I have to apply f. So f of 2 is going to be what? 2 squared, correct? And the result is 4. So f follows g of 5 is 4. So then hopefully you start to see that this idea of composition of functions isn't as complicated as it may have sounded at first. Now we're just applying two functions in sequence. That's all it is. It's a sequence of applications of functions. Now in this case, I'm applying the sequence in the other order. I'm saying first, what's f of 5? So what I'm doing is I'm applying the function inside the parentheses first. So f of 5 is what? 5 squared, which equals 25. So this will be g of 25. And then I'm going to apply g, 25 into the g function, which will just entail me subtracting by 3. And so the result is 22. So g of f of x equals 22. So far, so good. Are we clear with how to approach this? Okay, good. So it's really just a sequence. Knowing knowing how to interpret this kind of notation, knowing what to apply first and what apply after. That's composition of functions. Okay. All right, let's look at another example. This time, it's not going to be as straightforward. So f of x equals the square root of x, and g of x equals the square root of 2 minus x. And we're going to look for several things. We're going to look for f of g. And I also want to figure out the domain. So what is the domain for this function? Well, first, what is this function? What does it look like? Well, I'm applying g of x into f of x. That's what I'm going to be applying. So what is g of x? G of x is the square root of 2 minus x, right? So I'm applying the expression radical 2 minus x into f. What is f? What does f do? It takes the input and takes the square root of that. So that's going to look kind of strange, isn't it? So what do you mean is I'm taking the square root of the square root of 2 minus x. Now that is strange. That's a strange function. I told you it's going to get weird. Has anybody seen a square root with the square root inside of it? Well, it's totally in the realm of possibilities for it to happen. There's nothing that stops me from saying, hey, take this function and then apply the next function, and then I get this weird function. But we're not going to leave it this way. The square root, remember what is the square root as a fractional exponent? So if I want to rewrite this as fractional exponents, what is the square root? How else can I express the square root? If I raise it to what power? When I take the square root, right? There we go. Now we're talking. Yeah, it's to the 1/2 power. So isn't it okay if I do this to the 1/2 power? And isn't it okay to also do this 2 minus x to the 1/2 power? So I have something to the 1/2 power raised to the 1/2 power. But then what do we notice about 1/2 times 1/2? These are two exponents that can be multiplied. 1/2 times 1/2 is 1/4. So when you take the square root of the square root, you're really taking the 4th root. And that's f of g of x. Done. Again, you've never seen this function before? That's fine. But that's what the function is. Now the real interesting question is, what's the domain of this function? That's really the tricky part. We did the easy part. What's the domain? So first I have to find what's the domain and range of f and g. So first of all, what kind of functions are these? So we have to start becoming more comfortable with being able to identify the functions that we're given. They're not just random functions. That's right, Andrew. This is a square root, and both of them are square root functions. This is the parent function, right? The square root parent function. So we should already know what that looks like. We know that domain of f, right? We know that the graph for this function is going to look like this. So then what's my domain here? My domain here is going to be 0 to infinity. Those are my x values, right? All my x values are here. So they go from 0 to infinity. Now, what are all my y values? Domain of f. I mean, the range of f, pardon me. So the range is also 0 to infinity because it's everything on the y-axis. So far that's 0 to infinity, 0 to infinity. Now, what is the domain of g? And what's the range of g? So just to give us get more familiar with each of our functions. So what is the domain of g? Remember how we find the domain of g? Right. So what is the domain of g? What are the x values that make this okay? Well, the denominator has to be what? The denominator has to be
greater than or equal to
greater than or equal to what?
0.
Correct. Correct. So then we say 2 minus x has to be greater than or equal to 0. So what does x have to be? So if you solve this, what do you get? X has to be less than or equal to 2. So what's my domain? My domain is negative infinity to positive 2, including 2. That's my domain. And then what would be my range? So one thing you should notice is that this function, the g function, is also a square root function. It actually is a transformation of this function. But what kind of transformations were done? Actually, what was applied was a reflection across the y-axis and then a shift over to the right by 2 units. So actually, I get something like this. And you can graph this just to on your calculator just to make sure that it's the same thing. And so you realize that the domain is indeed from negative infinity to 2, including 2, and the range would be 0 to infinity. Now, let's be mindful now of what this function, how we created this function. What came first? G, didn't it? So G, immediately, my domain is immediately starting off to be negative infinity to 2. And my range is 0 to infinity, right? So the domain of G produces this range. And now this range has to see, I have to see if this coincides with the domain of my other function. And it just perfectly does. So there's no discrepancy with the range of G and the domain of F, which indicates that what is my domain of the entire function? What would you guys say? What would you guys think that the domain is? 0 to infinity? Try again. Remember, remember what we start with. Where is our starting interval? What is our starting interval? It's not 0 to infinity.
Negative infinity
to
0, including 0.
to 2. That's what we start with. These are the only x values that work for us and from the very beginning. So that's what we care about. What are the x values that I can plug in here? We'll first have to go through the G line. So you can think of G and F like security clearances. So this is one line of security, and then this is the second line of security. So what can go through G? Well, the only thing that can go through G are all the x values between negative infinity and 2. That's the only thing that goes through first. And then you produce this amount, right? And then what can go from here to here? Well, everything that is produced from G can go into F. So that's good. But what did we start with? We started with all the x values being between this region, and then everything cleared out afterwards. So therefore, the domain from the very get-go is the domain that we start out with, which is negative infinity to 2. So remember, it's the domain. We're not considering the range. The range would be 0 to infinity. That would be my range. The range that I produce would be 0 to infinity because that's what I produce at the end. So the idea is that this here is like the connection that exists between F and G. But again, we're just looking for the domain. And I know it's a little bit to think about. It takes a little bit of time to think about this, but it's about taking the pieces together separately and then seeing how you connect them. Okay, does that make sense? All right, so that's f of g. Now, what if I do, let's see, what if I do the opposite way, g of f of x? What is this? This is g of f of x. So g, I'm going to plug in what to g? Well, f is square root of x. So this is the square root of x. I'm plugging in the function square root of x into my function g, which is what? The square root of 2 minus x. So then what's going to be my function? It's going to be the square root of 2 minus the square root of x. And that's it. I'm going to leave it this way. This is it. I don't have to change it into rational exponents. There's no need for that. So g of f of x is equal to the square root of 2 minus the square root of x. That's it. And again, this is like the easier part. Now, what's the domain? We already discussed the domain, right? We already discussed the domain of f and g. We already did that. But what do we start with first? We start with not g. We start with f. What is f? F is 0 to infinity. I'm just going to write it again. 0 to infinity. And the range is what? 0 to infinity. Now, what's the domain of g? It's going to be negative infinity to 2. And then what's the range of G? Zero to infinity. Now, what is the problem here? This is what I start with, right? Start. And then look at my range. This is my output, 0 to infinity. But what's the problem? Does the outputs, do all the outputs of F fit into the inputs of G? Well, obviously not, right? 0 to infinity does not fit into the interval negative infinity to 2. So there's a problem here. There's a problem. That means, what does this mean? So the range of F does not fit. So I'm just going to say that. The range of F does not, quote unquote, fit into the domain of G. Now, what does that entail us to do? That means we must do what? Restrict the domain of F. So in order to make this smaller so that it can fit here, I must do something to the original domain. So it's not going to be 0 to infinity. I have to restrict it somehow, some way. Now, how would I do that? Well, I can think about this graphically, and that can be a bit more confusing. But let's go back to the original problem at hand that we have here with the function. What do we know about square root functions? Whatever is underneath must be what? Whatever is underneath the radical must be greater than or equal to 0. So we know the following. We know that 2 minus the square root of x must be greater than or equal to 0. It must be. Which means what? If you solve for this, what do you get? You get that the square root of x is less than or equal to 2. Which means what? Which means that x must be less than or equal to 4. Does everybody follow that? Does everybody see that x must be less than or equal to 4 in order for this expression to be greater than or equal to 0? So do you see how we're going to restrict our domain? My x values must be less than or equal to 4, but from the very beginning, my x values cannot be less than 0. So then what does that mean? How do we restrict our domain? So we restrict domain. All my x values must be less than or equal to 4, but at the same time must be greater than or equal to 0, because that's what the beginning. It must be greater than or equal to 0, but we have to restrict it because this doesn't fit into this. This range does not fit into g of x. So we have to compare what happens. So what we do is we take this expression and we know for a fact this must be greater than or equal to 0, and then we realize that x must be less than or equal to 4. But we started from the very beginning that x must be greater than or equal to 0. So this is my domain. So everything between 0 and 4, that's my domain. That's my domain. So everything from 0 to 4 would work. Anything outside of this interval would not produce anything. It would be either it would produce a number in the range of f that is not here, and so we can't even proceed with the composition of functions. Interesting stuff, isn't it? So it's not as simple as it may seem. Yet you have to take things into consideration, take it step by step. A lot of this is step-by-step stuff. Okay? All right. Cool. Now, one last thing that I want to do with this is that I can also, for example, I can apply f to itself or g to itself, like we talked about in the very first example of last class at the end. I can call this f and then apply f to itself. That's the cool thing about composition of functions. I could just do it to itself. And then you may ask, hey, can I do this more than once? Yes, you can do it as many times as you like. You can just do this 100 million times if you like. Apply f to itself, apply f then g, then f then g, then g, then f then. I can do this as much as I'd like. So what is f again? F is what? Radical x, right? So I'm applying radical x to itself. So I'm getting what? Radical of radical x. So this is really going to be now, because it's radical, then I'm going to rewrite this, right, as to the 1/2 power, and this is x to the 1/2 power. This is going to be what? X to the 1/4 power, which is the same thing as saying the 4th root of x. So that's f follows f of x for this problem. And then what would be the domain? Well, again, go back to the domain of f. And what's the range of f? It's going to be what? 0 to infinity, 0 to infinity. But then I'm applying it again to itself. So all of the outputs coincide with all of the inputs. So then what's my domain? 0 to infinity. So that's like an easy one because it just fits so perfectly. Okay. Is this understood? Is this clear? Any questions about this? Composition of functions business. So it's in a very, very extremely important concept for functions. Yeah, the domain is a bit confusing at first. You have to look back at this and see why it is so. Again, the domain, remember, what is the domain? The domain is the set of all x values that do what? That when you plug into the function, gives you a corresponding y value. Or in other words, the domain is a set of all input values that have an associated output value. So we have to understand the domain and range of both functions. When is the domain not 0? Well, you just have to make, well, these functions are not that complicated, so therefore 0 is going to be part of it. And because our functions are square root functions, 0 is an essential part of the domain. So when is it not 0? You would have to come up with the function that whose domain excludes 0. Yeah, so Tanzila. How do we know it starts off at 0? Well, that is because we understand, or we should know, the parent function of, or the graph of, this is the graph of y equals the square root of x. This is something that we have to understand and know. The square root of x, the graph of it is exactly this graph. And what do we know? The x value underneath must be greater than or equal to 0. Henceforth, the domain is 0 to infinity, including 0. And then henceforth as well, the range is 0 to infinity because I move all the way up to infinity from 0. Right. So I know it's a lot. So the problem is there's a lot of information you have to process at once. Like it has to be synchronized at once. So when you see square root of x, when I see square root of x, I don't just see square root of x as symbolically as you see it here. I also see it in my head as a graph. Then I have this full picture. I don't just have the function being written as f of x equals square root of x. Now I have a picture in my head of the graph, and this graph doesn't change because this is what's called the parent function. This is something that its basic knowledge. It's a basic unit of knowledge, and from this parent function, I get everything else. I get every other transformation of this square root function. But this is like this is something I have to know from the very get-go, from the jump, and then I can build upon this. Then I can build upon it, and then similarly, I can figure out what the graph looks like by understanding that it is a transformation of this function. But again, it takes time and it takes practice to really see the minute, the small details, because these are little small details that can either easily be glossed over. But that's part of it. That's part of this whole idea. Okay, so now I want you to see, can we recognize a composition of functions? Prav, this is definitely on the next homework. So definitely, it's already there. It's already up too. So homework number 4, I believe, right? Yeah, homework number 4 is already up, and you have some time to practice with this. So let's say I have a function, and I know it's the 4th root of x plus 9. And I want to decompose this. So decompose this function as a composition of two functions. So find f of x and g of x. So now we're going backwards. Do you understand this? I'm going in the opposite direction. I'm given a function, and they're telling me now, go back and find the two pieces that make up this function. So does anybody know how we can do that? So what would be my g function, and what would be my f function, so that when I apply g and then f, I get this result, this cube root, the 4th root of x plus 9. And the thing is, the answer to this, the functions that you put here are not always going to be, there's not just one pair. There could be more than one pair that work. So it depends upon how you see it. So does anybody have an idea as to how we can decompose this? No? Doesn't make sense. So look, so what if I do this? One way to do this very simply is to, especially when we have radicals, is to see what's underneath the radical. Well, why don't we make that our function? This function g, you can consider it as your inner function. So what's the inner function? And then the function on the outside, that's going to be your outer function. So my inner function will be what? X plus 9. And what's my outer function? The 4th root of x. And do you guys see that if I plug in f, if I find f of g of x, do you see that this is f of g of x? And this will be f of x plus 9, which will be the 4th root of x plus 9, which is exactly what I wanted to begin with. So this is one pairing. This is probably the most apparent pair of functions whose composition gives me this. There are other pairs that also work. Like you could have made it a little bit more complicated. So this is one pair, right? This is one pair of functions. I'll give you just another one, and then you can think about the other ones if you like. You can also say, I can also write it as this, as we've seen, right? The square root of x plus 9, and then call f of x the square root of x, for example. And then if we apply f of g of x to these two functions, what do I get? I get f of g of x. I get what? F of the square root of x plus 9. Then I take the square root of x plus 9. But I already know what happens with this, right? It's to the 1/2 power. So it's going to be x plus 9 to the 1/2 power to the 1/2 power, which is what? X plus 9 to the 1/4 power, which equals the 4th root of x plus 9, which is exactly the big function f of x. Make sense? So again, what I'm saying is that these pairs of functions are not always just one that work. There can be more than one pair that makes the result after the composition of functions. Okay? So we know how to now apply composition of functions. We have an idea of how to find the domain of the composition of functions. We know how to evaluate composition of functions with numbers in them. And now we know how to, in a way, sense a decomposition of these two functions, how to decompose two functions. And so all I want to do now is how do we use graphs to evaluate functions, and how do we use tables? So using graphs to evaluate composition of functions. So I'm going to draw a graph to the best of my ability. So this is going to be y, this is x, and this is going to be 2, this is going to be 3, and this is going to be 1, -2. So I'm going to have something like this. And then this goes all the way like this, straight line. This is a piecewise function here. This is f, and then g. G is going to be 1, 2. This is 3. And then you go 1, 2, so 3. This goes up like this, and then makes a little circle here. This is at 2, and then this is going to be at 4. And we have a certain function like this. And this is -2. Okay, so we have this kind of weird function. We have two functions, f and g, right? And let's say I want to evaluate the following. So evaluate f of g of 2. So this doesn't, it's not that different than what we've done with the other example where we had the actual function being defined algebraically. In this case now, my functions are not defined algebraically, they're defined graphically. But the idea is still the same. I'm going to find first, what is g of 2? What is g of 2? How would you find g of 2? Does anybody know what does g of 2 represent? Right, x equals 2 on the graph, correct. So then if x equals 2, then what does g of 2 represent? G of 2, remember, represents exactly the y value of the function. So whatever the x value is, which is 2, what is the y corresponding y value? It's going to be 5. So then this is really what? G of pardon me. So g of 2 is right here. So this is going to be 2 comma g of 2, which equals 2 comma 5. So g of 2 equals 5. And so then I say this is going to be f of 5. Now the question is, what's f of 5 now? Well, so this guy has a slope of 1. Let me just say this is slope of 1, and this point here is 4 comma. So this, I have to give you better, clearer points here. This is 4 comma 2. So then the next point here will be 5 comma. If it has a slope of 1, this is 5. So now 5 here, comma 1 would be 3, right? So this is 5 comma 3. So f of 5 equals 3. Does that make sense? When we have the graph, we're looking for the x, then get the y value. Then that y value becomes the x value for the other function. Then we find the y value of that function by looking at the graph. So it's really the same idea, except that now we're using the graph instead of algebraically applying it. So that's how we use the graph to evaluate composition of functions. It's looking for the x, then the y, then the x, then the y. That's all it is. Do you see that? We plugged in 2, we found 5 to be the y value. Now this 5 becomes the input for the new function, and then we find the y value for that one. And then that is the final answer. Okay? Let's do one more. So this is one of them. And then another one, let's see. What is g of f of 0? So first of all, which one do we do first?
F
We
of
do our
0.
inside function first, right? So f of 0, what is f of 0? In other words, what is the y value associated with the x value of being 0 for the f function? It's 0. That's right. So I get g of what? I get g of 0. But what is g of 0? Now look at the g function. And what happens when I plug in 0 for x? What's my y value? 3. Again, it's 3. You see that? Do you guys understand this? That's all it is. That's all it is. If you understand the sequence of f, then g, if you understand you're looking for the x value first, and then the y value, and then that becomes the x value for the other function, then the y value, then it's clear. It should be clear as to how to proceed with this.
So the y becomes x of the other one.
Correct.
Okay.
Correct. That's really the core of this composition of functions topic. The output of one becomes the input for the other. Can you go over g of 2? Yeah, g of 2. G of 2 is the same thing as asking for what is the y value when the x value is 2. Well, when the x value is 2 for g, the g function, when x value is 2, what's my y value? According to this graph, it's 5, according to the graph. And now that output, which is the y value for the g function, becomes the x value for the f function, because that's what's happening, f of 5. Now 5 is the input for f. And I'm applying the same reasoning, except that now I'm applying it to the other graph, which is f. So what is the y value associated with f to this function where the line has a slope of 1 and it goes to this point? So then f of 5 would be just one more above 2, which would in this case would be 3. So the overall output over the entire course of the sequence of operations is 3. So therefore the result is 3. Okay? So good, guys. Good. You're making the right observation. So now what if I have a use a table? What if I have a table? So let's make a little table. So I got g, f of x, g of x. kind of like this because it's like a little game. It becomes a little game here. Okay, so welcome to my game of table composition of functions, I guess I can call it. Now, I want to evaluate, for example, f of g of 2. So I have this table, and what am I looking for? I'm looking for the value of the function f of g of 2. Again, what do we do first? The inside function. And what are we looking for? The output of my function g when I plug in 2 as my input. But what is my input? How do we interpret this graph? Well, my input starts with the x values, right? My x value is what? 2. Now, what's g of 2? Well, I look at the g row. When x equals 2, what's my g row? What's the value for g? In this problem, it's 5. Okay, so now that became a 5, right? This became a 5 inside here. Now the question becomes, now the output of g becomes the input of f. So now I go back to x, and now the input is what? 5. But when I put the input for 5, what's the output? 6. Clear? Makes sense, right? It's just like a little game. It's like following the leader kind of deal, right? It's like follow the leader. So what if I do something like g of 2? What if I write it this way? So I'm applying g to itself. Okay, so g of 2. I become like a robot in a way. This is kind of a robotic procedure. First apply 2 to g. Okay, I do this again, right? 2 goes to g. When x equals 2, g becomes 5. So this becomes what? G of 5. But then what is 5? What happens to 5 when I plug into g? I get 1, right? See, this is a fun little game. And then you can go crazy with this. You can be like, oh, I don't know. This becomes, you can say g of f of, no, I'm just gonna leave that way. So g of f of 3. This becomes g of f of 3. What's f of 3? Well, let's go to the 3. 3 becomes 5 when I plug it into f. So this is g of 5 again. And g of 5 we already know equals 1. Do you see this? It really is just follow the leader, follow the x's and the y's and the x's and the y's. That's all it is. I hope that's clear. I hope it's understood. There's nothing out of this world, this idea of composition of functions. Okay. I'm glad it's starting to make sense. It takes time, guys. All of this. If you want to understand anything, especially mathematics, you don't understand it the moment you see it. You understand it when you yourself play with it, or as they say, play with it, or you get exposed to it. Over time, it kind of just makes sense eventually. But you have to spend time with it. You have to deal with it. You have to play with it, tinker with it. You have to, in order to really get a good intuitive understanding of what all this stuff is. But again, this is a very, very special and crucial part to understand about functions, that we can apply these kind of operations to functions. I can apply one function and then put into another function. That's a very powerful operation. Okay, so now that we have that understood, we're going to talk about what are called one-to-one functions. I should say, we're going to talk about one-to-one functions, and in the same breath, talk about what are called inverse functions. And understanding composition of functions is extremely crucial to understanding one-to-one functions and inverse functions. So first, let's define what is a one-to-one function. Does anybody know? A one-to-one function. Why is it called one-to-one? What does that mean? Does anybody have an idea? What is a one-to-one function? No? Haven't heard of this? So a one-to-one function is a function. So immediately you should think everything that I know about a function, I know that for every x value, there's one y value. So a function, a one-to-one function is still a function. So every x value has only one y value. But in this case, every y value is only associated, is associated to one and only one x value. So now we're going in the opposite direction. Remember what we said? Every x value can only have one y value. And remember when we talked about how the x values cannot repeat, but the y values can repeat for a function? In this case, one-to-one functions are all those functions whose x and y values cannot repeat. So in other words, y values cannot be repeated. That's it. That is a one-to-one function. So I'm gonna give you an example of a one-to-one function, and I'll give you an example of what's not a one-to-one function. So for example, if I take the square root of x, the parent function here, this is a one-to-one function. Why is it one-to-one? Because for every y value, there's only one x value. So this is one-to-one. Y equals f of x is one-to-one. Now, what is not? We'll take this into consideration. The parabola. Does anybody see why this is not a one-to-one function? This is not one-to-one. Why is the parabola not one-to-one? The y value repeats. What does that mean? Can you give me an example? How does it repeat? Like, what do you mean by repeat, though? One, 4, 9, 6. Yeah. What about those numbers? What about those numbers? Those are good numbers. But right. So it's squaring the x, but be more specific. You're almost there. You're almost there. So we have 1, right? We have 1, and then we have 4, right? What's the idea? What's the problem? What makes it not one-to-one? Well, for example, the 1, what are the x values that make it equal to 1? Aren't there 2 of them? You see that? And then how about the 4? Don't we got 2 of them? That's the issue. The issue is that f of 2 equals 4. F of negative 2 equals 4. So then if you write the coordinates, what happens? 4 is repeated twice because it has 2 x values associated with it. I have 2 x values that have the same y value. I have I have 2 different x values that have the same y value. Therefore, not one-to-one. because I want every x value to only have one y value and every y value to only be associated to one x value. And this is not the case. So therefore, y equals x squared is not 1-to-1. Does that make sense? So that's the reason why. For the y value 4 of 4 has two different x values, namely x equals -2 and x equals 2. No good. And so if you start to notice, one way to recognize whether a graph is 1-to-1 or not is very simple. We apply the horizontal line test. So you know with functions, you have the vertical line test to determine whether it's a function or not. Well, to determine whether it's a 1-to-1 function, we just apply horizontal line test. So if the line crosses, if the horizontal line here that I draw crosses it more than once, automatically not 1-to-1. And if you notice, if I draw any horizontal line, what happens? I cross each vertical horizontal line only once. So this is the horizontal line test. So this test is a test to determine whether a graph represents a 1-to-1 function. So if vertical lines, not vertical, if horizontal lines intersect a graph more than once, then the graph is not 1-to-1. And otherwise, the graph is. Okay? So if every line crosses it once, it is. If one line crosses it more than once, one horizontal line crosses the graph more than once, immediately it is not 1-to-1 function. Okay? So that's what it means to be 1-to-1. Now, why do I care about 1-to-1 functions all of a sudden? Well, I care about them because what I really care about are called inverse functions. So the idea is that, the big idea is that every 1-to-1 function has an inverse function. That's it. That's the idea. If you have a 1-to-1 function, then there exists the inverse. So what is an inverse? The inverse function just does the opposite. The word inverse really means opposite. So it does the opposite of the original function. So I'll give you a very quick example. And you've seen this already, right? We draw these two circles, right? So then I have 1, 2, 3, 4, 5, 6. This is the domain of, I'm gonna call it F, and this is the range of F, okay? And then I'm gonna make these connections. 1 goes to 6, 2 goes to 4, 3 goes to 5, right? This is a function F. What am I saying? I'm saying that F of 1 equals 6. I'm saying that F of 2 equals 4. And I'm saying that F of 3 equals 5. That's the original function that I get, right? But what if I want to talk about the inverse? I want to talk about the inverse. Now, the notation for the inverse function is given by f, and you put a -1. This is not an exponent. Let me just say this. This is not an exponent. This is just a notation, not an exponent, just a notation for inverse. That's all it is. So then what's the notation tell me? It tells me that if I apply f inverse of 6, I'm doing it backwards now. I'm going backwards. Now, this here is the domain of f inverse. And this here is the range of f inverse. Do you see how they swap? They swap the x's and the y's. I don't know if you've heard of that before. They swap the x's and the y's. So now my function, my inverse function, goes in the opposite direction. So my inverse function goes in the opposite direction like this. And I'm going to draw this like little dotted lines. So when I plug in 6, what is the output in my inverse function? It's 1. That's all it is. And when I plug in 4, what is the result? 2. And when I plug in 5, I get 3. You see that? That's why it's important to understand what a function is from the very beginning, because then you apply that idea, and now all you're doing is now going backwards. Now you're taking all the y values, making those the inputs, and all the x values originally become the y or the outputs for the inverse function. Make sense or no? So what about f? What are the relationship? What's the relationship between f and f inverse? Well, the first thing is you swap x and y values. The domain of f equals the range of f inverse. The range of f is equal to the domain of f inverse. Another thing, a huge thing, is the graphing part of it. The graph of f inverse is the reflection of the graph of f across the line y equals x. So for example, let's use the graph that we talked about already. Right? Y equals x, square root of x. Then if I draw the line y equals x, which is this diagonal here, and I reflect this line, if I were to reflect it, then the graph would look something like this. It's literally symmetric. This would be the inverse. So let me call this we call this f of x. So let me just say y equals f of x. Make it easier. So y equals f of x, and this would be y equals f inverse of x. That's what it means to be the inverse. It means that your graphs are reflected across the line y equals x. And if you reflect it across the line y equals x, it means that you swap the xy values. If you swap the xy values, that means that you change the domain and range for each. So this is like the big idea behind inverse functions. This is the graphical perspective of inverse functions. And then there's an algebraic perspective. The algebraic perspective is that if I compose, you see, this is why we talk about composition of functions. If I compose my functions, whichever way, whether I apply f and then f inverse, or if I apply f inverse first and then f, what do you think happens when I apply one function to its inverse? If I do this composition of functions? Anybody have an idea? No. So when you apply the inverse function to an original function, you cancel out. The very notion of inverse is the opposite. So if you apply a function and then you apply the opposite function to it, then you just canceled whatever you did in the beginning. So then the result is x. It's untouched. It's like saying you started from square one from the beginning, which is x. X is square one. That's the first thing you plug in. You undo what you just did, so you started with from the beginning. So that's the algebraic perspective. So algebraically, we think of it as f and f inverse cancel, quote unquote, each other. That's what it means to algebraically interpret inverse functions. When you compose them as a composition of functions, they cancel each other out. So if you have this understanding of inverse functions, then you would have a much bigger, I guess, view of why we even consider inverse functions. And inverse functions are also a huge part to understand the rest of the functions that you learn, because when you talk about, for example, exponential functions and logarithmic functions, they happen to be inverses of one another. When you talk about trigonometric functions like sine and cosine, they have inverse functions themselves. So this idea of inverse functions is very, very crucial. So a last little thing here is how do we find the inverse of a function? And this is algebraically speaking. So an example, right? An example. Let's say I want to find the inverse for f of x equals 3x minus 2. So what I do is I'm going to rewrite this as y equals 3x minus 2. And then I'm going to swap x and y. So when I swap the x and the y's, what do I get? I get x equals 3y minus 2. So all I did was I rearrange wherever I see x, plug in y, wherever I see y, put x. And then the next thing I'm going to do is solve. Solve for y. And then just rewrite using f prime, f inverse. So if I solve for y, I add 2 on both sides. I get x plus 2 equals 3y. Divide by 3. And then I get that y is equal to x plus 2 over 3. And then if I want to rewrite this now, I'm writing this as the inverse because that's exactly what this is. This is the inverse function. So if I have my function 3x minus 2, the inverse would be x plus 2 over 3. Okay? And if I compose those two functions, the result will be x, meaning that it cancels each other out. Okay? Does that make sense? Did we have a good time understanding one-to-one inverse functions, composition of functions? You're going to be hearing me say functions the whole way through. So any questions? Oh, well, I'm glad, Felipe. I'm glad you had some fun. Again, this is just the beginning for this. We're just giving the groundwork and the foundation to understand functions. Okay, so we'll stop here for today. And